Humans are different. We have different personalities. Each of us has unique traits that make us who we are. Some of us are introverted, while others are extroverted. We have different tastes, preferences, and ways of expressing ourselves. This diversity is what makes human interaction so rich and fascinating. We act differently in groups. Our behavior can change depending on the social context. In a crowd, we might feel more anonymous and act differently than we would alone. When we are with friends, we might be more relaxed and open. This variability is a fundamental part of human nature. But what about atoms? Are they all the same? At first glance, atoms might seem like simple, identical building blocks. However, just like humans, they have their own unique characteristics. Or can atoms have different personalities too? Can they behave differently under various conditions? The answer is yes. Atoms can exhibit a range of behaviors depending on their environment and interactions with other atoms. Atoms are the building blocks of everything around us. They form the matter that makes up our world, from the air we breathe to the ground we walk on. Despite their small size, they play a crucial role in the structure and function of all things. We often think of them as tiny, identical spheres, but this is a simplification. In reality, atoms are far more complex. They have a nucleus made of protons and neutrons, surrounded by a cloud of electrons. These components can vary, leading to different types of atoms with unique properties. But the world of atoms is far stranger and more interesting than we might imagine. They can bond together to form molecules, create complex structures, and even change their state under certain conditions. This dynamic nature makes the study of atoms endlessly fascinating. Just like people, atoms can behave differently depending on their circumstances. Their interactions can lead to a variety of outcomes, from the formation of new substances to the release of energy. Understanding these behaviors is key to unlocking the mysteries of the universe. This is where the fascinating world of quantum mechanics comes into play. Quantum mechanics explores the behavior of atoms and subatomic particles, revealing a world that is both strange and wonderful. It challenges our understanding of reality and opens up new possibilities for science and technology. Let's take iron as an example. Iron is one of the most abundant elements on Earth and has been used by humans for thousands of years. From ancient tools and weapons to modern skyscrapers and bridges, iron has played a crucial role in the development of civilization. We know iron as a strong metal used in buildings and bridges. Its strength and durability make it an essential material in construction and engineering. The steel frames of towering skyscrapers and the sturdy beams of bridges are all made possible by iron. But iron also exists as rust, a flaky reddish-brown substance. Rust forms when iron reacts with oxygen and water, leading to corrosion. This process can weaken metal structures over time, making rust a significant concern in maintaining the integrity of iron-based constructions. The difference between these two forms of iron lies in their electrons, the tiny particles orbiting the atom's nucleus. Electrons determine the chemical properties of an element, and changes in their number can lead to different forms of the same element. Iron can lose 2 or 3 electrons, becoming Fe2+ or Fe3+ ions. These ions have different properties and play various roles in both industrial applications and biological systems. Fe2+ is found in hemoglobin, the protein in red blood cells that carries oxygen throughout our body. Hemoglobin's ability to bind oxygen is crucial for transporting it from our lungs to tissues and organs, enabling cellular respiration and energy production. Fe3+, on the other hand, is responsible for the reddish-brown color of rust. This form of iron is less stable and more reactive, leading to the formation of rust when exposed to moisture and air. Understanding these different forms of iron helps us appreciate its versatility and importance in both technology and biology. Electrons occupy specific regions around the nucleus called orbitals. You can think of orbitals like apartments where electrons live. Each orbital has a specific energy level. According to the rules, electrons should fill the lowest energy orbitals first. But sometimes atoms break these rules. Copper is a great example. Copper has 1 electron in its outermost orbital when it should have 2. This rule-breaking behavior gives copper its unique properties, such as its excellent electrical conductivity. Section 4. Carbon's triple play, diamond, graphite, and graphene. These 3 forms of carbon are not just scientifically fascinating, but also have a wide range of applications in our daily lives and advanced technologies. Carbon is another element that showcases the diverse personalities of atoms. It can bond with itself and other elements in numerous ways, creating materials with vastly different properties. Carbon can exist in several forms, each with distinct properties. From the soft, slippery feel of graphite to the dazzling hardness of diamonds, carbon's versatility is unmatched. Diamond, the hardest known natural substance, is made entirely of carbon atoms bonded in a rigid, three-dimensional structure. This arrangement gives diamonds their incredible strength and brilliance, making them highly valued in jewelry and industrial applications. Graphite, the material in pencils, is also carbon, but its atoms are arranged in layers that can easily slide past each other. This layered structure makes graphite an excellent lubricant and a crucial component in batteries and other technologies. Then there's graphene, a single layer of carbon atoms arranged in a honeycomb pattern. This unique structure gives graphene remarkable properties, making it one of the most exciting materials in modern science. Graphene is incredibly strong, flexible, and an excellent conductor of electricity. Its potential applications range from flexible electronics to advanced medical devices, promising to revolutionize various industries in the near future. Section 5. The Quantum Future: Medicine, Materials, and More. Understanding the quantum behavior of atoms has huge implications for the future. In medicine, scientists are developing new drugs and therapies by manipulating atoms and molecules at the quantum level. Quantum computers, which harness the strangeness of quantum mechanics, have the potential to revolutionize fields like materials, science, artificial intelligence, and cryptography. Imagine designing new materials with unprecedented strength and lightness, or developing personalized medicine tailored to an individual's genetic makeup. Section 6. The Universe Within, Celebrating Atomic Individuality. The study of atoms is not just about understanding the building blocks of matter. It's about appreciating the complexity and diversity that exists even at the smallest scales. Atoms, like humans, are not simply identical particles. They have unique properties and behaviors depending on their environment and interactions. By embracing the strangeness of quantum mechanics and the individuality of atoms, we open doors to a universe of possibilities waiting to be explored.